So a fairly typical conservation of angular momentum problem. The idea with conservation of angular momentum is generally these problems, this is what happens. You have an object that is rotating, and it has therefore angular momentum. It has a rotational inertia of some kind times how fast it's spinning, its angular velocity. No big deal. And then through forces that are only internal, like nobody reaches out and pushes the object or whatever, that are internal to the system, the object manages, generally, this is the trick, is it changes its shape somehow, or it changes its distribution of mass, which changes I, the rotational inertia. Well, but I have to keep the same angular momentum. So if I change I somehow, then the object is going to start spinning faster or slower, depending on how you change I, to compensate for that, so that the angular momentum stays the same. And so the classic example, I'm pretty sure they mentioned in the videos that you watched, is the figure skater with their arms and or legs, with one leg outstretched, spinning slowly. When the figure skater brings her legs and arms, or his legs or arms, inward, reducing I, they spin faster. Why? Because the product of I times angular speed has to remain the same. So if you reduce I, you've got to raise the angular speed. Same thing for a diver, like somebody that jumps off of a diving board, right? And they want to spin. If they rotate with themselves extended, they rotate slower. They have a lower angular speed. But if they pull into the tuck position, if they pull their knees up towards their chest, they'll rotate faster. And they can really adjust their rotational rate to make sure their feet or head or whatever are pointed straight up or down when they impact the water, because by adjusting slightly their rotational inertia, by bringing their mass closer to their axis or farther from their axis. So in this problem, we have an angular momentum problem. Now, situation before and after, so let's do this. I have this carousel. Let's just consider it a spinning platform. If you've never actually seen something like this, some playgrounds have them. They're actually really not safe, but that makes them awesome. Is there just a flat piece of metal, circular metal, that is allowed to rotate, you can push and rotate around. So, and that's how I'm envisioning this problem, is that you have this disc of metal that can rotate. We're looking at it from above, and here's the axis of rotation. Whoops, making lots of little circles. Here's the axis of rotation. And you have a person. Here's your person, located at a certain distance initially away. And it doesn't matter which direction this thing is rotating, so we'll just say it's going this way. And then afterwards, so later, the situation changes because the person has moved in a ways. Therefore, the I, the rotational inertia, has changed. It had an initial rotational inertia, and now it has a final rotational inertia. By moving some of that mass towards the axis, you've changed the value of I. Now, since the angular momentum initially has to equal the angular momentum final, that's the overall idea here, what will happen is your angular speed will change. You have an initial one, and it will become something different afterwards. So, what we need to figure out is, we need to start looking at how would we figure out what the rotational inertia is before and after. Is that something we can calculate? I don't think so right off, because I think they ask us for the mass of the person. But I think they give us these two, here and here. And so basically our idea here is that since the original angular momentum has to equal the final, all the forces are internal, I originally times omega original equals, and our final I is going to equal right? Okay, got that. Final I times, so our final momentum is final angular, rotational inertia times final angular velocity. Now, This is no big deal. Here and here, two numbers, they give them to us, no big deal. Here's where the fun is. What is, for a person riding one of these, what would be the angular inertia? Well, they give us the angular inertia of just the carousel. And that's one, they just give us the number, 125. And that won't change. But we treat the person as a point mass. The person's, so as a single point mass, the person's I, so person, I'm going to put a 1 here, initially, a little 0, initially, is going to be his mass or her mass times the radius initially squared. In other words, this distance here. But when he or she moves in, there is a new or final radius. It's smaller in this case. And so at this location, the I for the person finally is going to be the mass of the person times that final radius squared. And any time that you have to find the rotational inertia or the moment of inertia for something, you can, if it consists of multiple parts or you can break it up at least conceptually into multiple parts, you can just add the various inertias. So in other words, this is going to be, initially, it's going to be the rotational inertia of the carousel plus the rotational inertia of the person initially. And afterwards, since the carousel didn't change, it's that plus the rotational inertia of the person afterwards, which is slightly different because of the change in radius. So, this is going to be I carousel plus I person initially. And this is going to be I carousel plus I person finally, after they move. So those get expanded out. Now, let's do this. Let's go ahead and distribute the angular velocities. So, and let's expand out this and this to represent the mr squared for the person. So we're going to have omega 0 times IC, so I distribute that times here. I'm going to multiply this times that, but at the same time, I'm going to expand this. That's going to be times the mass of the person times the radius, the distance from the person to the axis of rotation, initially squared. mr squared is we treat the person like a point mass here. So the same thing over here. Final angular velocity, IC, plus final angular velocity times m, same mass, same person, but now the radius is different. Final radius squared. Now, depending on how you want to handle this, you could continue with the algebra. I think now that I've got it to this point, there's only one unknown, and that's our mass. If you look at the problem, they give us, let's see, do they give us, yes, they give us this, they give us that. They give us this, and this, and this, and this, and this, and this. They give us everything but the mass. So you got a couple ways you can handle it, but I think at this point, let's go ahead and put in the numbers. I think it'll make solving for this a little easier for you if we do it now. So this is going to be, doing this from memory, 0.6 times 125. I should check that. Yep. Plus 0.6 times, I'm going to put the radius here, so that's going to be 1.5 was initially squared. And then I'm going to put the mass, my unknown, there. If I just switch the order of these, put one in front of the other. Equals 0.8, the final rotational speed, radians per second, times 125, the carousel didn't change, plus 0.8 times 0.976, is that what it went down to? Should check that. 0.967. Squared, don't forget to square that, times m. And we'll push the buttons on this. I'm going to pause this, and I'll be right back. And almost seemingly instantaneously, bam! I've pushed all the buttons on the calculator. If you need to pause the video at this point and do it yourself, make sure you get the same thing I'm getting so far, feel free. I'm going to forge on here, because you can always shut me up anytime you want. So, that's the beauty of this, isn't it? You could just... Anyway, so I'm going to subtract 75 from both sides. Giving me, let's see, 25 on the right. And then I'm going to subtract 0.748 from both sides. Make sure I did that right. 1.35 minus 0.748. So I got 0.602 m equals 25. And if I divide both sides by that 0.602, I get a mass of 41.5 kilograms. Seems reasonable. Let's see if it's right. Yep, there we go. So, feel free to go back over this problem again, but the idea here is, the overarching idea is the I is going to change. But the angular momentum, in this case, is going to stay the same. Has to. Conservation of angular momentum holds because everything was internal. Somebody didn't run up from outside the carousel and push it with an external torque. So we can assume that this is equal to this.